So let's get started. I'm so excited. I hope you had plenty of coffee because in this lecture, we are going to take a deep dive into physically based rendering. Now, there is so much ground to cover that it is even hard to decide where to start. But I think that a good entry point is discussing what PBR materials are used for. Now, PBR materials are an industry standard. It's a pipeline that has been developed to create realistic looking materials, realistic looking renderings in all sorts of fields, from VFX and movies to advertisement and video games. Now, I've used PBR to create realistic previews of materials, realistic assets and textures for digital production, and realistic photo shoots for my own designs. And like the name suggests, physically based rendering is based on physics. And so, as I have emphasized in previous lectures, the difference between a hobbyist and a high-level professional is often a deep scientific understanding of how things work. Now, to understand PBR, we must start with light, more specifically, the photon. Now, the photon is an elementary particle that is a quantum of the electromagnetic field. In other words, it's like the basic unit of light. And sometimes, as a quantum particle, it also behaves as a wave. And this is known as the wave-particle duality, which has been demonstrated with a famous experiment in quantum physics known as the double-slit experiment, which is the one you're seeing on screen, and it sort of demonstrates that photons, that light has wave-like behaviors and exhibits wave-like properties like pattern interference. Now, as far as we are concerned, for the purpose of our conversation, what is of interest is that one of these wave-like properties is the wavelength. So light can have wavelength, which is a measurable distance between two wave peaks. And this aspect of light is essential to understand color and color theory, and therefore later on PBR, or physically based rendering. Now, the electromagnetic spectrum encompasses all wavelengths of the electromagnetic radiation. However, what we understand as visible light or color is just a narrow portion of this spectrum, like a narrow range of wavelengths that roughly goes from 380 nanometers to 750 nanometers in wavelength. Now, understanding this for us is important because specific wavelength correspond to specific perceived colors. And this kind of like forms the foundation for our next topic as we move away from quantum physics and start to talk a little bit about human biology. So, as the light enters the human eye, as you can see in the top right corner, we have an illustration that sort of abstracts a little bit the structure of the human eye. As the light enters, it is refracted by the cornea and the lens and travels towards the retina, which is at the back of the eye, and eventually meets the optic nerve that connects to the retina. Now, on the left, you are seeing a real picture of a human eye, and that kind of like bright spot is the optic nerve. What is of interest for us is that instead, if you look in the bottom right corner, we have two different illustrations. They might look similar, but there are sort of major differences in the design, if you will it. So on the left, we have the structure of the human eye, whereas on the right, what you're looking at is the structure of the eye of the octopus, which, speaking about evolution, has developed in a sort of parallel way. So the problem of vision, the problem of how to see, has been resolved in terms of biological features with two different independent designs. In the way that our human eyes are structured, because of the way that the optic nerve connects to the retina, it creates a blind spot in our vision, a spot where there are no photoreceptors, like we are literally blind. But this is not a universal feature. In fact, as I was telling you, the eye of the octopus, which is structured differently, doesn't have a blind spot because the optic nerve connects from behind the photoreceptors and not in front of them. Now, I'm telling you all of this mostly because you don't go around with a black hole in your field of vision, right? In fact, this might be the first time that you're hearing about the fact that you do have a blind spot, dead center, or so to speak, in your field of view. And you don't notice this because what your brain does, it sort of like compensates and artificially create information that fills in the gap. And so this is important for our conversation because it highlights the fact that the phenomenon of vision does not end when the light hits the eye. There's so much of vision that is actually constructed by the brain as it interprets the visual stimuli. Now, if you want to have a direct experience of this blind spot, it's fairly easy. All you have to do is close one of your eyes. So, for example, if I'm closing my left eye, I'm gonna, with my right eye, look at the corresponding letter, in this case, R. And basically, you wanna place your open eye at a distance from the screen that is approximately equal to 3 times the distance between the R and the L. Basically, move your head closer or away from the screen, and at some point, you will notice that the other letter will just disappear. It will stop being in your field of vision. And that is happening because at that specific point, the information around that part of your field of view that the brain is picking up is what's being used to sort of like fill in the information, and what the brain is using is causing it to completely omit the existence of the L letter. Again, this is super important for us as visual creators because it means that what people see is not always what is physically there. There's so much of perception that it is constructed and not simply received. And as a visual creator, that's the field where you are operating. That's where you make the magic happen. Now, moving forward, another important concept that we need to understand is that while there are features that are commonly shared, so all humans have a blind spot, there are, however, other aspects that have much greater degrees of variability and subjectivity. And so we can now start to talk about the photoreceptors in the retina. So as we said, as the light enters the eye, it eventually reaches the retina and the optic nerve. And the retina has photoreceptors, which, as the name suggests, receive photons. Now, there are two kinds of photoreceptors in the retina. There are rods and there are cones. Now, rods are highly sensitive to the light intensity, but not color. And so that's why you are able to see in the dark when your eyes get adjusted to it, because you have highly sensitive rods in your eyes. And at the same time, rods are responsible for you being able to perceive and understand depth, together with the fact that you have two eyes that are creating what's called stereoscopic vision. But color comes from the cones, which, if you look at the pictures to the right, which are real pictures, the cones are those slightly bigger bumps that you see. Now, cones themselves come in three types, and if you will, each type is tuned to a different region of the visible spectrum. So at the beginning of this lecture, we pointed out how specific wavelength correspond to specific colors, and now we can understand why. So the cones that are attuned towards short wavelengths are the cones that perceive the color blue, whereas those that are attuned towards the medium wavelength perceive the color green, and those that are attuned to the long wavelength perceive the color red. In fact, if we look at this graph here on the left, we need to understand that we are not perceiving the entirety of what we call the visible spectrum. We have peaks of sensitivity, and those peaks are determined by the fact that we have three kind of cones that are tuned to different wavelength: short, medium, and long. Now, because there are three peaks, this is called trichromatic sensitivity, which forms the biological basis for how we normally perceive color. So while some aspects of vision are common across every human, so every human has a blind spot, other aspects like the sensitivity to color is highly subjective. It changes from individual to individual. In fact, it might even change between your left and your right eye. You might have different distribution of different types of cones that will cause the perception to be slightly different. For example, you might see with one eye colors as slightly of warmer tones, and with the other eye you might see things as of a slightly colder tone. Now, to some extent, cones are tied to the X chromosome, and so for that reason, although it's not the only reason, some individuals might have what is called color blindness. And there are so many types of color blindness. Color blindness is not just one. There are many types that basically mean that the peaks of color sensitivity are offset because mutations in the X chromosome have affected how cones work in the eye. And of course, because males have one X chromosome only, they are more often affected by color blindness than females. Now, of extreme interest is the fact that females having two X chromosomes can actually, in rare cases, carry four types of cones. So they have basically four peaks in their color sensitivity, and that's called tetrachromacy. So they can see like four peaks, which leads to seeing a wider range of colors. Anyway, all of this, apart from being extremely fascinating, is of interest because our technology is designed to match our biology, our biological vision system. And so what you need to understand, and here we're starting to get into color theory as it pertains digital production, monitors, any kind of screen or display technology are created using what's called RGB pixel, which stands for red, green, and blue. So the colors that you see on screen, again, are just red, green, and blue, teeny tiny lights that light up, and they are sort of like matching the sensitivity of the cones in the normal vision of the normal person, which once again, to remind you, it's a trichromatic sensitivity. And so once again, here we understand why having a deep scientific understanding of why things are made in a certain way is important, because this kind of knowledge affords us to be cognizant. It affords us the kind of insight and knowledge that enable us as creators to reach the highest forms of artistic expression. And so, to reiterate, here I have some optical illusions that will drive you crazy, but this is an example that highlights some aspects of vision that are common to everyone. And that is that it's not a trick, it's not moving, but you will be able to see white dots in the place where you are sort of like staring at, and they will disappear in your peripheral vision. And this is just because of the way your eyes are built. At the same time, there are aspects that are more psychological and at the same time are shared across all human beings. And so here we have two shapes. And if I were to tell you to ask to associate which one is the boba shape and which one is the kiki shape, each one of you will associate the sound kiki to the shape to the left, which is more angular, and the sound boba to the shape to the right. And once again, these are all very well studied scientific phenomena that highlight commonalities between all humans, and at the same time, our perception and vision do not end with what is physically perceivable, but also there is a major part that has to do with the brain trying to make sense of the information that it is receiving. At the same time, there are other aspects that are highly, highly subjective. And so, for the vast majority looking at the screen right now, will be plain as day that of these bars, if you were to count from the left to the right, the sixth one is of a slightly different color. However, if I were to show you this one, it would be probably a much smaller portion of the viewers that will be able to see plain as day that, again, if you count from the left to the right, the fourth one is of a slightly different yellow. And that is because each one of us has slightly different sensitivities on color. All right, let's get back into Blender now and open up the free project template, the first one. Make sure we are in rendered viewport shading so we can see some color, and also that we turn on the show overlays so we can see what we had selected. Then middle mouse click and we're stepping out of the camera. I am gonna shift select the pedestal and Suzanne, press H, hide them out of the way. Shift A, mesh, create a simple cube so we can get started. G, Z to bring it up. And now what I want you to do is to bring up this portion of the editor. And if you don't have it on shader editor, you can change it from the top left icon. So make sure you are in shader editor, and on the right in the properties panel, you want to click on the last tab that we've seen in previous video, the material tab. And now again, with the cube selected, we're gonna press on new, and this will create a shader for us, which is the first step in creating a material. As you can see, by default, it will be named material, and you will have some properties here that you can control. But to have much more control, what we'll do instead is that we will create the material directly into the shader editor. And if you're not seeing anything, like in this case, what you can do is follow the same exact steps that you would follow when you are lost in 3D space, and that is press A as in all, and that will select all nodes that define the material. Then press full stop on the numpad, and that will bring you home. And in this case, it will bring into view the basic nodes that constitute any PBR material. So what you're looking at is the principled BSDF shader and the material output. So BSDF stands for bidirectional scattering distribution function, which is a mathematical function that describes how light interacts with a surface. Now, for the purpose of what we are doing at the moment, the first few concepts that you need to grasp are that we are now inside a shader, which is another word to talk about a material. And more specifically, the shader is what is assigned to the object. And inside the shader, we have a bunch of information that specifies what kind of material is being rendered. Then that information is passed from the principled BSDF to the material output, which is what makes it so that you can visualize it into the 3D viewport. In fact, if you were to click with your left click on this socket and disconnect this, you will see that the cube will turn pitch black, because now, although the principled BSDF exists and has information in it, the information is not being passed to the output. Now, the principled BSDF is sort of the most popular node that you will use in shaders, as it allows you to create most materials. It sort of features a collection of the properties that you're most likely going to need to describe a material, and it fits all of them into one compact node, and from there you can create almost any material. Now, the first one, of course, is the base color, which if you click on the color swatch, with the left click, will pop up this menu. And the first thing you see is that there is a color wheel, and if you click anywhere, it's gonna reflect that change immediately. And you will also see that not only it is synced with the principled node, but also to the right in the properties panel. In fact, you could do the same from here. Now, just below, you will notice that there are two tabs, RGB and HSV, which stands for hue, saturation, and value, which are also the settings that you see just below. In fact, if you click on the other tab, this menu will change and it will show you the red, green, and blue channels. Now, the technical execution of it, it's so simple that you might think, well, we could have just opened up Blender and gone straight into this, but then you wouldn't know why is it that we have a red, green, and blue channel. Instead, now you know that these values are turning on and off the tiny LED that compose the display, and then you know that that technology, that hardware has been engineered to match the biology of how human eyes work and perceive the electromagnetic spectrum. And so not only now you have a much deeper appreciation of how this thing is actually working, but as you go about making more complex stuff later on, you will have a deeper intuition of what is really happening and most importantly, why. Now back to the menu, I'm gonna left click on the red channel, drag down all the way to blue and let it go. Press 1 so that everything is at maximum, and now we have white. So when all the three channels are at the maximum, we have white, and when all the three channels are at 0, we have black, absolute black. Now the channel below, that is called an alpha, stands for transparency or sometimes opacity, where when the value is at 1, you have full opacity, meaning that the object is fully visible, whereas when you have it at 0, it's non-opaque and it becomes transparent. However, we will cover this in more detail later as it is kind of tricky. Now, moving on, if you were to change again back to the HSV tab, you will see that the values have now changed. In fact, RGB, HSV, and also this string of letters and numbers that it's called a hex are all different ways in color theory to represent a specific color. Now, bear in mind that this is referring to digital color. What you are controlling here is how the combination of red, blue, and green LED lights up on a display. So it is tied to the hardware of the display that now you understand. So playing around a little bit with it, if I were to turn on all the way up the red channel, of course, we have everything lighting up in red. The same goes for each individual channel. And as you combine them, you will see that the color wheel will sort of move in between. Now, a little pro tip for pursuing photorealistic looking renderings is that nothing in the real world is absolute white or absolute black. Even if you take the whitest white on a snowflake, that still wouldn't be an absolute one across all the channels. And at the same time, if you picked up the blackest piece of charcoal at night, still it wouldn't be fully black. For that reason, if you go and check out the spheres I set up for you, the true white, I have set it up at around 0.8 and the true black at 0.01. Now, the instances in which you will have to be absolutely physically correct about this will be very few. So truth be told, you can pick somewhat arbitrary values just as long as you don't go all the way to absolute 0 or absolute 1, because that will result in something looking a little bit off. Back to our cube, just to give you a brief introduction to also hue, saturation, and value. If I have a channel, say the red channel that is all the way up, changing the hue will rotate this sphere along this circle, basically going across the spectrum of visible colors until it circles all the way back again to red. The saturation, on the other hand, will drive the sphere towards the center where you don't have color, whereas value will make it so that whatever value is at the center is across the grayscale. So you can think of that as almost the luminosity of the color if it is bright or dark. Now the reddest red, or the purest color you will have, regardless of which one you pick, you will have it when your value is right in the middle at 0.5, which if the saturation was at 0 would be a middle gray. But when you have the saturation at the maximum, that's when you have the purest color. Now this may be a little bit less intuitive in the beginning because you would think that you would need to have the value at 1. But if you noticed, as I brought it up to 1, that red kind of washed away and lost what is called purity. It sort of like became a little bit less intense. It became more of a pastel tone. But I think that probably at this time you had enough color theory for one day. So let's move on to the next property. So the next one is the metallic property, which is an abstraction to create metallic looking materials. The pro tip here is that for photorealistic renderings, this should be either at 0 or at 1, because in the real world, an object is either metallic or not, and the look of it actually depends on the behavior of the electrons in the physical material. So as you bring this up to 1, you will see that the object starts to look more like a metal, and it starts to reflect a little bit the environment around us. This sort of works in tandem with the next property, which is roughness. And roughness is a property that abstracts the quality of the surface, whether it's rough or very smooth, whether it's porous or absolutely polished. So if you bring this down to 0, you will have an almost mirror-like effect. Whereas if you bring this to 1, the object will be almost not reflecting anything of the environment in the way that you would expect to see on the surface. Although it's still interacting with light. It's just that the way that light is bouncing off of it is so all over the place that what's reaching your eyes is no longer forming an image that you would reconcile with how the environment looks like. Again, here the pro tip is that in real life there are no extremes. This is sort of an abstraction. So in real world, there's no object that is absolutely, totally mirror-like polished. And so you should never use an absolute 0. And also you should not use an absolute 1. Just keep away from the absolute extremes. Now, if we play a little bit with it, at around 2, we have a somewhat polished metal that starts to look kind of nice. And this would probably be a good time to switch from a cube to Suzanne. Now, I've applied the same exact material onto the Suzanne monkey head. And as you can see, it looks so much more interesting. So probably now you can understand why we have in the first place a mesh like Suzanne, because the moment we start to work with materials, it is important to have complex surfaces that allow us to understand how the material will behave under different circumstances and shapes. So, continuing our exploration, if you were to keep the roughness at 0.2, which is kind of low, but turn off the metalness and then maybe bring the value all the way to 0.3, you can start to see now that we have something that looks like a semi-glossy gray plastic. If we were to bring this to an extremely low value, we would then have a super, super glossy, almost enameled plastic, or maybe something that is wet. Whereas if you bring this up to something like 750, you would start to have something that it starts to feel almost like matte plastic that has a more opaque reflection. Now, before we move to the next option, which is the IOR, I wanted to point out that if you select the true metal sphere, you will see that there is a different node called metallic BSDF. Now, this is a more recent node that is, as the name suggests, focused only on metallic surfaces. And this allows you to create more precisely metals. More specifically, you can tune parameters so that you can recreate the look of specific metals. And as you can see, you have similar properties like the roughness, which here I have left to an absolute 0, and you can play with it to see how it changes. So as you see, as it goes up, the rougher the surface becomes, the more it starts to scatter back the light in ways that disrupt the original image that's being reflected. And eventually your eyes can no longer make out the picture and it starts to look as a not so polished surface. Now, we will not cover in detail the options of this node in this video, but this is just to point out and reinforce the fact that all of this work is based on real physics and real physics calculation and modeling of interaction between light and surfaces. Now, back to the principle BSDF, the next one is the index of refraction, that previously was also known as specular, and it is still listed as specular in other software. Now, this parameter might feel confusing at first, but the index of refraction controls how the rays of light refract from an object once they hit it. In simpler terms, what it does for us is that it provides us with a parameter that we can tune to tweak how much our material is interacting with light. So to give you a demonstration, if I were to bring the roughness all the way up, and if then I brought value of the color to the most absolute black, you will see that still you can kind of make out what's happening here. And that is where index of refraction comes in. At this stage, your material is still very much interacting with the light. However, if the index of refraction was to drop to 1, then you would have something of a black hole where the light and the material are not really interacting anymore for the purpose of what we're doing here. Now, in Blender, an index of refraction of 1.5 will be the default, but know that specific materials have specific indexes of refraction. For example, the one for water is 1.33. So as you start to pursue making realistic materials, you will have to look up what's the exact index of refraction of that material based on the physics from the real world, and that will allow you to create the most realistic results. Moving on, we have the alpha, which, as I mentioned earlier, refers to the opacity or transparency of the object. And so as this drops down, the object starts to become less and less opaque and more transparent. Finally, we have the last parameter that we will cover today, which is the normal. Now, to truly understand the normals, you first need to understand the one big concept of PBR. And that is that all of this is just a game of passing parameters within a range. In other words, the paradigm under which this abstraction of the PBR pipeline has been constructed is that you have values that float between a range that goes from 0 to 1 in most cases. And then that value that floats between 0 and 1 can be passed as information to any of these sockets almost interchangeably. Now, to demonstrate this, I have this set up right here where I have two values, 1 and 0, and I combine them into a vector. Now, a vector is a mathematical object that allows you to put together multiple values while also keeping them separate. So in this case, I have one entity, like one container, one box, and within it, I have the information that x is equal to 1 and that y and z are equal to 0. Now, the concept that I was trying to pass is that all of this information right here is just values. All these dials are just values between 0 and 1, and you will start to bend this to your desires. And the more you learn about it, the more you can get creative and sort of break almost the rules to make this thing do impossible things. Now, the proof is here. As you know now, color is based on the perception of three wavelengths, which in digital representation become the three channels R, G, and B. And right now we have a pure red because we have the value of 1, 0, and 0, which is the absolute exact thing as if you were to pass a vector into it with the same values. And if you were to put 1 and 1 and 1 everywhere in the vector, that would be an absolute white. So this is the one key concept to truly mastering PBRs and the principle BSDF, and that is that it all boils down to values between 0 and 1, between black and white. Now, things like colors and normals are vectors that need three values, and that's why they are color-coded differently, whereas the other values have gray inputs because they take in single values. And as you can see over here, the value also has the same color coding with a gray dot output. Now you could have a value like this and plug it into metallic, for example, and say that it's 1 and would be the same thing as passing the 1 over here. You could then plug this and send it to roughness, and now the roughness is at 1. Now, the reason why you need to understand that it all boils down to zeros and 1 is because 1 stands for white and 0 stands for black. And so while the sliders over here allow you to input one value that it's sort of like affecting the whole material in a uniform way, when you start to introduce textures in the picture, you now have the option to introduce values locally. So right here, I have a checker texture that is black and white. And although it is black and white, this could also be thought of as a value where it's white, it's 1, and where it's black, it's 0. So if you were to plug that information into the metal slot, then you would see that now some parts are metallic and some are not. And this is fundamental to understanding the normals, because now we are going to put every piece of information that we had together. So when we have a normal, we have in most cases a texture that could be either an image or a generated texture, like the checker texture that we just saw. And that texture is creating the same effect of zeros and ones, although it is doing it on 3 separate channels, leveraging the same paradigm of the red, green, and blue. The purpose of this is that the normals provide the computer with additional information of how the material would behave with light. More importantly, it allows you to create the illusion of more complex materials instead of having to actually 3D model them. So in this case, we are looking at the tiles of the wall in the background, and rather than having to individually model all of those tiles with real 3D meshes, which would be computationally expensive and also would take a lot of time, we can instead resort to an image to create a believable result. And all of this is created by providing the information to the computer of how the light would behave across the X, Y, and Z channels. For this reason, normals are the most instantly recognizable textures, because they will always have a very prominent blue channel, which confers them this violet bluish look to it. Now, the normals, to go through these calculations, need to pass through a specialized node that tells the computer that we are no longer using RGB but XYZ, and that's the normal map node, which then plugs into the normal slot. And now we have a very odd looking Suzanne monkey hat that somehow has the texture of a tiled stone wall slapped onto it. Now this is so much information, and it is okay if it takes a minute to click in. The only thing that I'm gonna do before wrapping this up is to demonstrate once again what we just said about the normals. So normals are images, and if you plug them into the color, you will see that they look like the image on the right. In fact, it's the same exact image, and they always look like this kind of color because they have a prominent blue channel. They are leveraging the fact that we have 3 channels, red, green, and blue, but they are sort of hijacking this pipeline to instead convey X, Y, and Z information about the 3-dimensionality of the material. And if I pass it into this node, separate X, Y, and Z, I am splitting those channels individually. And you will see that now that I have individual channels, they look like grayscale, with each one being slightly different because they refer to different axes. Okay, you made it through. So that was a tremendous amount of information. This was a super highly technical, highly theoretical lecture. And it is okay that it takes a moment to sink in. In fact, the moment that we will start to put everything into practice in the next video, everything will click. But now you know so much, not only how things work, but why. So to do a brief final review, you now know that light has wave-like properties, one of them being the wavelength. Because of this, our eyes are tuned to three specific peaks of wavelength, and because of that, we mostly see red, green, and blue. And because of that, our technology, our displays are built to reflect that. And because of that, when we move from the hardware of the display to the software, the way we control how those LED light up or not is through three channels, with those three channels being the R, G, and B. However, those three channels individually are just values that float between 0 and 1, like a grayscale from black to white. And therefore, because they're just values, at the end of the day, you can plug one value into one socket or another and it will just work. The only difference being that some parameters take in single values and other parameters like the colors or the normals take in vectors, which are bundles of three values at a time. And so when you plug it into the colors, you have RGB colors showing up. And when you plug it into the normal, you are actually instead passing XYZ information to create the illusion of an even more realistic surface. Now, once again, congratulations, because although this is a super long, super dense lecture, you have just covered more than most people gets to understand after years and years of just playing around with things without never going to the why. Now, I'll see you in the next video, which, like I've said before, will be focused on 3D modeling. And so rest assured, it will be all hands-on and just fun.